In this lesson, I'm going to describe Big O notation. You can use Big O notation to study the performance of algorithms. Normally, Big O notation looks at the upper bound on an algorithm's performance, so you're looking at its worst-case behavior. For many practical uses, that's the safest way to look at an algorithm's performance. If an algorithm has a good Big O performance, then you don't need to worry about it blowing up on you when you use it in a program. Big O notation also looks at an algorithm's asymptotic behavior. By asymptotic behavior, I mean the algorithm's performance as the size of the problem grows very large. Often people use the value n to represent the size of the problem. So another way to describe asymptotic behavior is to ask yourself, what happens to an algorithm's performance as n grows very large? For example, suppose you want to sort a list of numbers, and you have a couple of different algorithms that you could use. If your list only contains 2 numbers, so the size n equals 2, then it doesn't matter which algorithm you use. It's hard to imagine any method taking more than a few microseconds on a computer. Now suppose the list contains 10 numbers, so n equals 10. That's still not a very big list, so whatever algorithm you decide to use will be fast enough. Suppose the list contains 100 numbers, or 1,000, or maybe 1,000,000. Now things start to get interesting. It's still not all that hard to sort 1,000,000 numbers on a computer, but now the algorithm you pick might actually make a difference. Some sorting algorithms are much faster than others, so some might sort this list in a few seconds, while others might take a few hours. This is what I mean by asymptotic behavior. Big O notation looks at an algorithm's performance when the problem size becomes large, because that's usually the only time we care too much about the algorithm's performance. So how do you figure out an algorithm's Big O notation? You can do that by following 5 rules. First, if an algorithm performs f of n steps for some mathematical function f, then the algorithm has order f of n performance. It's written like this, Big O, paren, the function, close paren. It's usually pronounced order f of n. For example, suppose you want to find the largest number in an array of values using this simple algorithm. The algorithm initializes the variable max to hold the first value in the array. It then loops through the array of values. If it finds a value larger than max, it updates max to hold that value. For an array containing n items, the loop performs n steps. That means this algorithm has order n behavior. Here the function is simply the linear function f of n equals n. Here's the second rule. If an algorithm performs f of n steps followed by g of n steps, then it has behavior order f of n plus g of n. For example, consider this algorithm for finding the maximum and minimum values in an array of values. The algorithm starts as it did before to find the maximum value. Then it repeats roughly the same steps to find the minimum value. First it performs n steps, then it performs another n steps, so its behavior is order n plus n, or order 2n. If the algorithm performs some steps followed by some more steps, you can add the behavior of the 2 sets of steps. The third rule says, if the function f is larger than the function g for large problems, then you can simplify f plus g to be just f. Basically, this says you can round up. Because f is larger than g, eventually the function f will dominate the runtime, so you could ignore g. For example, suppose an algorithm performs order n squared steps, followed by order n more steps. The function n squared is bigger than the function n for large n, so this algorithm's performance is order n squared. To see why that makes sense, let's plug in some numbers and see how many steps the program is executing. When n is 10, n squared is 100, and n squared plus n is 110. At that point, the extra n accounts for only 10% of the total number of steps. When n is 100, n squared is 10,000, and n squared plus n is 10,100. Now the extra n term adds only 1% to the total. When n is 1,000, n squared is 1,000,000, and n squared plus n is 1,000,001,000. Now the extra n adds only 0.1% to the total. You can probably see where this is going. As the problem size gets larger and larger, the extra n steps contribute a smaller and smaller percentage to the total. If you were using the algorithm in a program, the amount of time spent on those extra n steps would mean less and less. For example, if n is 100,000 and the program takes an hour to run, then the extra n steps adds only about 1/3 of a second to the total. It's just not worth worrying about. Notice that this rule also means you can ignore constants that are added to a function. For example, order c plus f of n for some constant c is the same as order f of n. That's because the constant c is also a function, it just has a constant value. Because a constant is smaller than any function that increases as n increases, you can ignore the constant. That's rule 3. If the behavior depends on the sum of 2 functions, you can ignore the smaller function. Rule 4 says, if an algorithm performs g of n steps for each of f of n steps, then its behavior is order f of n times g of n. For example, this algorithm determines whether an array contains two identical values. The for-I loop loops through the array. Nested inside that loop, a for-j loop also loops through the array. Within the inner loop, the program compares the values at positions I and j. If the values are the same and I isn't equal to j, then the algorithm returns true to indicate that the array contains the same value twice. Here, the for-I loop runs through the n items in the array. For each of those items, the for-j loop also runs through the n items in the array. That means the algorithm's behavior is order n times n, or order n squared. That's how Rule 4 works. If an algorithm performs g of n steps for each of f of n steps, its behavior is order f of n times g of n. The last rule says you can ignore constant multiples. That means order c times f of n is the same as order f of n, and the order f of c times n equals order f of n. This rule is a bit harder to understand. Suppose one algorithm performs order n squared steps, and another algorithm performs order 2 times n squared steps. Even when n is large, the second algorithm will still take roughly twice as long as the first algorithm. In this case, the big O notation doesn't really let you compare those two algorithms. However, it does let you compare them to other algorithms that have different big O notations. For large n, both will be slower than order n algorithms, and both will be faster than order n cubed algorithms. In practice, you may need to experiment to pick between two algorithms that have the same runtime behavior. For example, there are many sorting algorithms that have order n times log n behavior, but some are considerably faster than others. Those are the rules for big N notation. They may seem a bit confusing now, but they should get easier after you use them for a while in later lessons. If you're a graduate computer science student, you need to apply the rules carefully and precisely. For this course, however, you can use the rules in a